Can we start? Okay. Let's go over a bit of what we did last time near the end of the hour. We got into continuous time LTI systems. And one of the things is that everything pretty much moves in parallel to the discrete time story. But there are some nuances and some differences that I'll point out as we go along. One property of discrete time LTI systems that you came to understand was that they are completely characterized by their inputs to an impulse. And the same story holds in continuous time. If you have a continuous time LTI system, and you give that system an impulse input, you get some kind of a response that we call the impulse response of the system. And it turns out that that impulse response characterizes pretty much what the output will be if you change the input to some arbitrary signal, x. And that's because x, any signal x, can be written as a linear combination. Notice in continuous time, our linear combinations very often turn out to be integrals. Linear combination of shifted impulses, where the x of tau is the values of the signal at particular dummy variable instance in time, scale the corresponding impulses, and you can write the signal as this linear combination. Well, if this system is LTI, and you know its response to a particular input, and you can write a more general input as a linear combination of these inputs, shifted and scaled, then clearly you can write the output corresponding to this arbitrary input. So let's go through that step by step. If the response due to delta of t is h of t, what is the response due to delta of t minus tau? H of t minus tau. And if I now multiply this by some number, what's the corresponding output? My time variable is t. This is a dummy variable, so this acts like a constant. X of tau, h of t minus tau. Now, if I take a linear combination of these in the form of an integral, so I allow tau to vary. And so instead, in the discrete time, you had a summation of x of m delta of n minus m. Here you have x of tau, tau being the dummy variable, delta of t minus tau from minus infinity to infinity. Then the corresponding response will be what? The system is LTI. The same integral of this guy on this side. Minus infinity to infinity, x of tau, h of t minus tau d tau. And by the shifting property of the impulse, you know that this integral is equal to what? This impulse picks the value of this signal at the location where the impulse is non-zero. For what value of tau is this impulse active? T. So this must be equal to x of t. If that's the general input to the system, then this must be the corresponding output. Okay? Everything follows through from linearity and time invariance. And of course, you recognize this integral from one of your problem sets as the definition of the convolution of x and h. With a simple change in variables, you can turn this around and write it as h convolved with x. So if you let, for example, let mu be t minus tau, then d mu will be minus d tau, and you can work it out and write this integral as the integral from minus infinity to infinity of h of mu x of t minus mu d mu, which is h convolved with x. Okay, so that's the story in continuous time. Everything, again, follows through from linearity and time invariance. Now, last time I went into the frequency domain. So this is all in the time domain. And in the frequency domain, I said, OK, let's consider an input of the form e to the I omega t, some complex exponential of frequency omega. And what happens at the output? And we worked it out. So let's take this form of the integral, of the convolution integral. So y of t is the integral from minus infinity to infinity, h of mu. We may have had tau in the last lecture. It doesn't matter. It's a dummy variable anyway. H of mu times x of t minus mu. What is x of t minus mu? E to the I omega t minus mu. Anywhere you see a t, you replace it with t minus mu. And this is d mu. Okay? Now, there's a part of this complex exponential that has no mu dependence. And that's the e to the I omega t. So I can remove it from the integral. And I'm left with the integral from minus infinity to infinity, h of mu, e to the minus I omega mu, d mu, this whole thing, times e to the I omega t. And what did you recognize this as? H of omega. This is the frequency response of the filter. So a complex exponential of a particular frequency went in. The same complex exponential came out, but now it's scaled. So to the extent that h of omega is non-zero, this signal will appear, this complex exponential will appear in the output. If the filter happens to kill that particular frequency, if h of omega is 0 for that particular frequency, well, then obviously this doesn't turn up. Conversely, if a particular frequency is not present in the input, there's no way it's going to show up in the output, right? Because let's say I have x of t equals e to the I omega 1 t plus e, or not t, plus e to the I omega 1 t. But this one has a 0 in front. When we say this particular omega frequency omega 1 is not present in the input signal, it's as if I say there's a coefficient of 0 in front of it. Right? What comes out? H of omega naught e to the I omega naught t. So again, to the extent that this is not 0, you'll see omega naught in the output. But what about the second term? 0 times h of omega 1 e to the I omega 1 t. So this is going to be 0. Okay, so that's why we say LTI systems cannot create new frequencies. LTI. Now I'm going to make the general statement. So before I only said this about discrete time system, LTI systems. So now I'm going to say it about all LTI systems. LTI systems cannot generate new frequencies That's one point. The other point is that complex exponentials are eigenfunctions of LTI systems. And by that we mean in discrete time, we had e to the I omega n go in, and h of omega e to the I omega n come out. So whenever a complex exponential goes in, it just comes out scaled. And in discrete and continuous time, e to the I omega n goes in. Yes. T goes in. H of omega e to the I omega t comes out. That's what we mean. Okay? Now, I want to highlight one major distinction between frequency responses of discrete time LTI systems and continuous time LTI systems. So one distinction. In discrete time, you had h of omega was the summation of h of n e to the minus I omega n, where this summation went from minus infinity to infinity. In continuous time, you have h of omega. Notice I'm making a deliberate point by putting in different dummy variables just to prevent you from getting fixated on one variable. In continuous time, we have this expression for the frequency response. In discrete time, when we shifted the frequency response by 2 pi along the frequency axis, what did we get? We got it the same thing back. So you had h of n e to the minus I omega plus 2 pi n. So wherever you saw omega on the right-hand side, you replace it with omega plus 2 pi. And you had so now you rewrite this, n h of n e to the minus I omega n and e to the minus I 2 pi n. And what do you know about this? It's 1. And because it's 1, you get this equal h of omega. Okay? It's 1 because this n is an integer. Now, when you go to continuous time and you look at h of omega plus 2 pi, you get integral h of t e to the minus I omega t e to the minus I 2 pi t dt. What can you tell me about that? Is that identically 1 for all time? No. In fact, that's a particle that goes around the unit circle at the rate of 1 hertz. One revolution per second. Okay, so certainly it's not always sitting on the number 1. This is not identically 1, except for certain t. And so in discrete time, we had the situation where all you had to do was plot the frequency response over an interval of length 2 pi. And because this function is periodic, you didn't have to worry about all the rest. But here, in continuous time, when you're asked to plot the frequency response of a filter, you have to do it for all frequency, minus infinity all the way to infinity. Okay? So that's very important. So in continuous time, in discrete time, we plot h omega over an interval of length 2 pi. In continuous time, we plot over all omega. Now, these distinctions aside, I want you to constantly be aware of the parallelism between continuous time and discrete time. Very often, all you have to do is convert a summation to an integral. And pretty much the relationships will hold. Okay? And use that to your advantage. So you have to memorize less. Let's do an example. So suppose I have a filter whose impulse response is e to the minus at u of t. All I need for this to be to have a well-defined frequency response is for the real part of A to be greater than 0. But I'll make it simpler for you. So here, just assume A is a real value, and it's greater than 0. Yeah? If A is a complex number, well, why don't we revisit this when we're through with finding the frequency response? Then it will make a lot more sense. Notice, whenever you have an infinite sum or an infinite integral, there are always convergence issues that you have to worry about. Does that integral converge? Does that sum converge? Okay. So stipulating this deals with that convergence issue. But we'll see that. So plug it in, look at what h of omega is, and tell me what you get. So just for now, assume it's a real valued quantity greater than 0. And if you want, you can plug in a particular number if it makes it easier for you. All right. So how are we doing? Are we there? Meatball. Jason? Go for it, Jason. So that expression is up there. Now, tell me what to do with the limits of the integral. Okay, so 0 to infinity. Why is that? Because of the unit step. So you... Huh? This is called the unit step function, yeah. Even in discrete time, it's called the unit step function.
Okay, so let's see. So then we have
e to the negative I omega t dt. Now what do we do? Combine the exponents. Now let me pause right there. Is everybody with us about the changes in the limits? Okay. And I changed the, okay, I merged the exponents. What do I have?
t times quantity a plus I omega.
A plus I omega t, and there's a negative sign. Don't forget the negative sign. dt. And what's that? I'm sorry, I didn't hear you.
E to the negative t times quantity, or e negative t is quantity a plus omega. That's all over negative a minus omega.
A?
Well, negative a plus omega. That's between 0 and infinity.
Okay.
So if you plug in infinity for t, you're going to get 0.
Now here's where the restriction I imposed on A comes into the picture. Okay. If you look at the numerator, let me split that numerator. I didn't mean to cut you off, Jason. Just one moment. I'm going to break that off. And we're going from 0 to infinity. Okay. When I plug in t equals infinity, this guy right here doesn't do anything other than go around the unit circle. Okay, it's always a finite value. It's not going to run away anywhere, right? And in fact, you don't know what the limit of this thing is as t goes to infinity because it's oscillatory. But thanks to this exponential, we know where the numerator is going to go when t is equal to infinity. If A is positive, as I've stipulated, then t is going to, as t goes to infinity, it becomes 0. So you have 0. Minus.
So if t is 0, then you have basically e to 0, which is 1. So it's 1 over negative quantity a plus I omega.
A plus I omega. Okay, and the negatives now cancel out, and you've got your frequency response. 1 over A plus I omega. If A had not been positive, this would have blown up. And this filter would not have had a frequency response. Now, all is not lost when A is positive. There is another integral that you'll learn about in EE 120 that's called the Laplace transform that deals with cases like that. But as far as this class is concerned, we're always going to deal with that integral, which, by the way, even though I haven't called it that integral right there in the top is the Fourier transform of small h. That's what we'll learn later on. Again, we have now learned both in continuous time and in previous lectures for discrete time how to hop over from the time domain into the frequency domain using this integral in the present lecture and this summation in discrete time, the summation in the top. So that summation and that integral at the top tell us how to go from the time domain to the frequency domain. We still don't know the way back, and that's for later in the course. But we can still say a heck of a lot about these systems by starting in the time domain going into the frequency domain and analyzing these systems in the frequency domain. So this is the frequency response of the filter that has that particular impulse response. And I will show you, hopefully we'll have time in today's lecture. I'll show you that that actually is the impulse response of a simple RC circuit. Simple resistor, simple capacitor in series. All right, should we take a break? Let's take a break. Okay, folks. Yeah. The news about the midterm? It's let's see. 4th, I couldn't get a room. Yeah, they told me you can't have a room on the 4th. So 4th was what day? It's a Tuesday. So count on the 5th. I mean, if we can't do it in an outside room, we'll do it in the class. 5th? Oh, 5th? No, that can't be right. We'll do it on the 4th. 4th. And 4th, I shouldn't have done it anyway. I didn't realize at the start of the semester that it's not a good day to have the exam. So 6th. How's 6th sound? Okay, I'll try to get a room for the 6th. And I have my office hours on Thursday nights anyway, so a lot of you have that space, that time frame clear. So we'll either do that. If I can't get a room for the 6th, we'll just do it in class on the 6th. Does that sound good? There will always be no's. I mean, okay. Let's plot the frequency response for this. I want to plot the magnitude response for this filter. And just as I pulled some shenanigans when I was dealing with discrete time filters, I'm going to write the obvious and the low entropy form I omega plus A into the higher entropy form I omega minus A. In discrete time, to measure or to plot the frequency response, we went around the unit circle. That was the place where we spent most of our time. In continuous time, we go along the I omega axis. This is also the I omega axis. And in more advanced courses, you'll see this, they call this the sigma or the real axis. So any number, in this case A, can be represented with a real part and an imaginary part. And I should not use A, Z, complex number, has a real part and an imaginary part. So the real axis is sometimes called the sigma axis, and the imaginary axis is called the I omega axis. For continuous time LTI filters, we measure the frequency response by walking along from minus I infinity to plus I infinity. It's not the unit circle that we worry about. So this is where we go along. Okay? Now, in this particular example, I have I omega, which is a point on the I omega axis. So let's say I'm here for a particular omega. And A was a positive real number, I told you. So minus A is sitting somewhere here. Minus A. You agree? Yeah. A and omega are real numbers, yeah. So minus A is here. I omega is here. And I omega minus A will be a vector. Where's the head of that vector and where's the tail of that vector? Head is I omega, and tail is right here. So this is the vector I omega minus A, which is I omega plus A. Okay? Now I'm traversing the I omega axis from all the way down here to all the way up there. And the magnitude of the frequency response is inversely proportional to the length of this vector. You see that? So where is that length the shortest? Omega equals 0. So what does that say about the magnitude at 0? It's the largest. Notice I don't put pi minus pi anymore, because I have to plot this thing over the whole omega axis. So at 0, I know I'm at a peak. And what is the value of that peak? When I'm here. Why am I hearing omega? Omega is 0 when I'm here. What's the length of the red vector? A. So it's 1 over A. And then, what can you tell me about the shape on this side compared to the shape on this side? It's mirror image. And as I go to infinity in either direction, how does the magnitude change? Goes down to 0. It asymptotically goes down to 0. To get the curvature right, you're just going to have to plot a few points. Okay? What kind of a filter is this? Low-pass filter. Now, if this had been the frequency response of some kind of an analog circuit, circuit designers have a definition for the bandwidth of the circuit. It's the frequency, and they call that the cutoff frequency. Cutoff frequency. Omega C is the cutoff frequency. It's the location where you are 1 over square root of 2 times the peak. Can't remember how many dBs that works out to, 6 or 3, one of those. If you have a scientific calculator, can you please figure it out? It's what? 3 dB. So basically what they're saying is, yes, we know that this frequency response is not exactly flat over this range. But we can tolerate this much degradation, but cannot tolerate anything more than that. So a rule of thumb, it's a heuristic, there's no objective reason for this, is that they consider the bandwidth of the filter to be this range of frequencies. And omega C is the cutoff of that filter. So the same geometric type of analysis that we did in discrete time has an analog for these kinds of filters, except instead of going around the unit circle and doing all those vector computations in your head, you go along the I omega axis and you eyeball things. Yeah? Yeah, I did address that point. There is no objective reason for that. It's a heuristic. That for practical purposes, in some applications, even this is not tolerable. In some applications, more than this is tolerable. It all depends on the specifications of your application. But by and large, in a lot of applications, you can tolerate this much degradation, a 3 dB degradation in your magnitude response, and still consider as all these frequencies as having been passed through roughly on an equal footing. Yeah? Yeah. Well, I mean, it corresponds to that, but for physical applications, why should all physical applications work out such that, all of them are half power? Everything between the half power points is acceptable. Yeah. Okay. Let's do another example. I'll come back to this. I'm going to show you how this is related to an RC circuit. Let's do another one. So let's say I have a filter whose impulse response is a window from minus A to A, and it's 1 in between. What's the frequency response? Just go to the definition. Are we there? Okay, Jason, you get to pick the next person.
Yeah, gentleman in the tan shirt into that row.
They're demanding your name. Eugene. A little louder, Eugene, so everybody can hear you. Okay, the integral goes from negative infinity to infinity, and how does that get changed here? negative a to a, because h of t is 0 outside this band. Okay? And in that range, h is 1. So what do I have inside the integral? Omega t dt. Okay? Over negative I omega. Negative a to a. Folks, only Eugene should be talking. Okay. Minus I omega a over negative I omega. I have a negative here. Now, how does that get massaged into something we like? Into a sign. This is now the opposite of the sign of a sign. So let's turn that, take the negative in the denominator into the numerator. I have 1 over omega. And what's left when I take the 1 over omega out? Omega a. And that's the frequency response of this filter. Let's plot that. So in the time domain, you have a box. In the frequency domain, you have, now how do you plot this? What does this look like? It's like a sink. It's a sine function that gets decayed according to 1 over omega. So at 0, what's the value, Eugene? When you take omega to 0, what do you get? You got to use Hopital's rule. To what? The derivative of the bottom is 1. So the derivative of the top is going to be a times the cosine, which goes to 1. So you have an a times the 2. So that's what the value is at this peak, 2a. And what's the first 0 crossing on either side? When does this go to 0 for the first? At what omega does this go to 0 first? Let's say on the right side. What does the argument of the sign have to be? Well, 0 we've already considered. When omega equals 0, you have the denominator also equal to 0. As soon as we move away from 0, we only worry about the numerator. The first time this sign goes to 0 after 0 is what? When the argument of the sign is what? Now forget about a. Just I have sine of alpha. Aside from alpha equal to 0, what's the next alpha at which it is 0? Pi. So the argument of this sign has to be pi. So omega has to be? Omega a must be pi. So omega is? Omega a must be pi. So what does omega have to be? Pi over a. And on this side, it's minus pi over a. and this is going to be 2 pi over a minus 2 pi over a, and so on. Now, what I want you to recognize, so let me just write the expression again here, is 2 over omega sine omega a. This is a very good example to illustrate the uncertainty between time and frequency. When your function in the time domain gets narrower, that happens when a is decreased. When I decrease a, this pulse width gets narrower in time. What happens in the frequency domain? It widens. Okay? And vice versa. When a is increased in time, when the pulse width in the time domain is increased, this thing tightens together. And not only that, the peak goes up. Can you guess what kind of a form h of omega will take when I take a to infinity? A what? A Dirac delta. So a limit as a goes to infinity of h of omega is some constant times the Dirac delta. Because this main pulse width decreases, this thing goes to infinity. It's exactly what a Dirac delta is. We don't know what this alpha is yet. It turns out to be 2 pi. We'll learn later that this is 2 pi, that alpha is 2 pi. It's a normalization constant that we'll learn about when we study Fourier transforms. But at this point, all you need to recognize, and you have all the tools to recognize this, is that when a goes to infinity, what kind of a signal does h of t represent? What kind of a function? A goes to infinity. What is this? H. It's a constant 1, right? How many frequencies are in the constant 1? 1. And what is that frequency? That's exactly what's encapsulated with this delta of omega. So there are multiple ways you can reach the same conclusion, and they all reinforce each other. And you should make use of these kinds of sanity checks. As a goes to infinity, what happens there? Okay. Yeah. Well, you can do it that way. You can get the height at omega equals 0 by plugging it into the expression, or by looking at the figure. The length of the red vector when I'm at omega equal to 0 is what? It's a, isn't it? From the origin to that x, the length is a. And the magnitude response is 1 over that. How did I get the 2? The 2a? Yeah, I got the 2a by applying Hopital's rule to this expression. At omega equal to 0, the numerator is 0, the denominator is 0. So you've got to apply Hopital's rule. You apply Hopital's rule. You have this 2 floating around anyway. Okay? And the derivative with respect to omega of the sine is a times cosine. The derivative with respect to omega in the denominator is 1. Now you evaluate this at omega equal to 0. Yeah? No, it's not the ideal low pass. The ideal low pass would be a sink in the time domain and a box in the frequency domain. This is the box in the time domain and a sink in the frequency domain. You're not equipped yet to do the other situation. Because if I had given you this kind of a function in the time domain, you can't plug it into that integral because it won't converge. So there are some shenanigans that happen. But this is a perfectly valid function in the time with that particular integral to plug in. But this, what does it look like to you? Where's the bulk of the... It's low pass. Yeah. But it does pass all these frequencies too. It's just that it's suppressing them. Low pass doesn't mean you don't pass high frequencies. Low pass simply means you prefer the low frequencies over the higher frequencies. So the amplification that you give to the lower frequencies exceeds the amplification you give to the higher frequencies. So this still qualifies as a low pass filter. Yeah. By the way, if you don't believe me, try a sink in the time domain and plug it into that integral and see if you get anywhere. I mean, you can actually see it by just replace this omega with a t. Let's say I had a t here, and I had an h of t here. This sign oscillates between -1 and 1, so it's always on the order of 1. This t in the denominator decays on the order of 1 over t. And you know from calculus that things that decay according to 1 over t don't converge. So when you plug it into the frequency response expression, you're not going to get anywhere. Yeah? Inverse convolution? There are deconvolution algorithms, but usually to do the inverse, you do it in the frequency domain. Yeah. But there is no exact deconvolution formula. Because you take, it's like saying 1 plus 3 equals 5. Can you get 1 and, oh, I'm sorry, 1. They didn't hire me because I could do arithmetic. You say 2 plus 3 equals 5. And then your question is, if you give me 5, can I spit out 2 and 3? Obviously not, because there are multiple combinations that can produce that. Yeah? This won't have a difference equation representation. Very good question. So this is an example of an LTI system that cannot be represented with a difference equation. No, it doesn't have to be infinite duration. Guidelines is that you typically impulse responses that can be represented as a linear combination of one-sided exponentials. That means you have an exponential, you get a u of t, or a u of minus t, or something like that. You have a linear combination of these. It gives you a differential equation. If you look at the first example, that's a one-sided exponential. There is a differential equation that represents that. And the RC circuit is exactly that. So I'm going to move toward this from another direction, and you'll see that the differential equation and the frequency response and the impulse response that is one-sided exponential all fit together in a nice picture. So let's get on with the RC example. Here's a series RC circuit. Okay? Now, again, we don't require you to know circuits. So whenever you need the input-output relationships of circuit elements, we'll give them to you. In this case, X is my input, YC is my output, the voltage across the capacitor. So for now, X is input, YC is output. the voltage across the capacitor at any given time is 1 over C integral from minus infinity to that time of the current that goes through that capacitor. In this case, that current I've represented with G. Notice I'm scrupulously avoiding I. It's one of the clashes we have with circuits courses, because we use I for the square root of negative 1. So the voltage across the capacitor is 1 over the capacitance times the integral from minus infinity to t of the current. But what is the current? Any ideas on how to get the current from the circuit? I don't want any G's floating around in my equation. The differential equation that I'm about to derive cannot have G's in it. It can only have the input and the output and the constant parameters that define the system. It's the voltage difference across the resistor divided by the resistance. The voltage on this side of the resistor is X. On this side, it's YC. So the voltage difference is X minus YC. And the voltage across the resistor divided by the resistance gives you the current. So let's write that. G of t is X of t minus YC of t divided by R. Or in other words, voltage is current times the resistance. Voltage across the resistor is the current through the resistor times the resistance. Okay? Now I have everything I need, because I can just plug this into the integral, and I'll have an equation that only involves the output that I'm interested in and the input. So I have YC of t equals 1 over C minus infinity to t x of tau minus YC of tau over R d tau. How do I get a differential equation out of this? Take the derivative of both sides. So on the left side, I have YC dot, which is the time derivative, first order time derivative of YC. On the right-hand side, I have 1 over RC times what? What happens when you differentiate this integral with respect to t? The what? X of t minus YC of t. And we have our the differential equation. So our differential equation is RC YC dot plus YC equals X of t. That's the differential equation that governs the system. When the input is X and the output is the voltage across the capacitor. Can you tell me what the frequency response is by fiddling around with the differential equation? Using a similar technique that we used when we dealt with difference equations. What was the trick there? To find H omega, I'm going to use HC just to recognize, just to highlight the fact that this is a frequency response from X to YC, not to YR, because that's another frequency, that's another system if you consider YR as the output. So to find the frequency response, what do? You plug in X of t is a complex exponential, and Y of t is HC omega e to the I omega t. So do that. Quick. You've got 2 minutes. Plug it in and tell me what H frequency response you get. Okay, what do we have? Eugene, you get to pick the next person. My condolences. I think only your neighbors can hear you, and certainly nobody heard your name. Christine. The derivative, okay, which is? Wait, 1 over, what are you taking the derivative of? What's the derivative of yc? With respect to time. This has no time dependence. This is the only time dependent factor. So what happens when you take the derivative with respect to time? HC folks, please cool it. E to the I omega t, and then what else? Over times I omega. And you plug that into the expression. So on the left side you have I omega hc plus hc e to the I omega. And on the right-hand side you have e to the I omega t. And now what? Cancel it. Folks, I'll let you go in a minute. It's hard enough to hear Christina as it is. Oh, RC. RC. And you cancel out, and you solve for HC, and what do you get? 1 over I omega RC. Now, I'm going to rewrite this for you so you can see the connection with the first example. I'm going to take the RC out, and you're going to be left with 1 over RC over I omega plus 1 over RC. What's the impulse response by comparison with the first example? What's A? 1 over RC. And you've got a constant factor in front, so that stays. E to the minus AT. T over RC times U of T. From here? Not unless you do the frequency response. And I'll talk about that next time.